Welcome back to Next Up, where we take a look at interview questions rather one by one than looking at a theme and finding different questions that pertain to it. So we take a look at one question and then have a deep dive on how to best understand it, and then form a 1 or 2 sentence answer such that it's concise whenever we have to use it in our interview. Today's question is, how do you combat the curse of dimensionality? So when you are faced with a lot of data in your data set, not all dimensions of your data might actually be useful for what you're trying to model or trying to fit. And with that brief introduction, let's have a look at the deep dive that today comes from towardsdatascience.com, published by Halina Olinik. Why and how to get rid of the curse of dimensionality right. First, why is it actually an issue? The curse of dimensionality and dimensionality reduction itself are necessary to be talking about. And the problem is that you have like a lot of data, and some of them might be highly correlated, and some of them might not contribute to your problem at all. And in order to tackle this, they go into deep depths here to actually just come up with all the different traits on how to tackle that. First up is like really simple, to just manually select the features that you want to keep. And they already like say it in the first sentence, if the data science is acquainted with the data set. So like if you basically have some domain knowledge, or if you know exactly in the data set what's going on in there and which data are necessary and which are not. Then we can basically just like select variables that we want to keep, and other variables might just be removed from the data set. You can get rid of useless variables right here as well by looking at their correlation. Those features that are like highly correlated basically show the same signal all over their like dimensions. And they basically show the same signal. You might as well just choose one in order to reduce your overall dimensionality and help with your modeling and fitting later. A very popular and other solution is using principal component analysis, which projects your data into like a different like set of basis vectors. So it finds your data set, projects your data set into a matrix T, and projects it using a different matrix T into that like space, into that how to say, coordinate system. That's what I wanted to say. So like the idea behind PCA is matrix factorization. So we have our data set and then have two matrices T and P transposed. We're projecting a data set into a matrix T. Is the same as assigning a scalar into every row and columns represented by dominant object patterns. Projecting a data set into a matrix P is the same as assigning a scalar value every column. Rows of it represent dominant variable patterns. Vectors T and P are orthogonal. So PCA can be formulated as a least squares module, with output x is the same as 1x, or 1 input x, plus TP t plus an epsilon. And epsilon represents the residual. So the basic thing is you have like something that's kind of skew in your original data system, and then you just rotate and scale such that it ends up being aligned with like the first 2 or first 3 axes of your coordinate system. Like the main axis of your data sets will align with the main axis of your coordinate system. And then like highly related to it is the singular value decomposition. Informally speaking, singular value decomposition is an enrichment of the principal component analysis, except for the fact that now columns in our matrix T are normalized to length 1. And we're having one more matrix D, which stores actual lengths of these vectors. And there are like a lot of nice visualizations on what a singular value decomposition actually achieves. And you can imagine like a skew ellipse that's being remapped into like a even circle. That's what SVD can actually achieve. So further down, they say matrix U is the same as T, but with normalized vectors, as it was mentioned earlier. D is the diagonal matrix having square roots of eigenvalues and covariance matrix XX as its values, and V is absolutely the same as P. So SVD is also the basis for other popular algorithms, they say. For instance, latent semantic indexing in terms of natural language processing tasks. Values of the matrix D are often referred to as explained variants of the components because they represent the importance of each of the variables. And usually, if you come up with the answer PCA or SVD, it basically invites the interviewer to just ask you straight ahead, can you explain PCA? Can you sum up SVD in 2 or 3 sentences, just walk me through the main process? And then it really helps to basically have a little deeper understanding of the math behind both of those algorithms as presented here on this webpage. Multidimensional scaling is another approach that you can use that basically applies a function f for each component of your dataset vector, and then therefore creates a like mapping algorithm that consists of 3 steps. First is a discrete representation by choosing some points of your dataset, coming up with the manifold distance measure on your discrete graph. And then your distance measures either you are connected or infinite otherwise. And then the distance, if you're connected, is like kind of the distance between those points. And then you kind of update your geodetic distance, and then you embed it into an isometric Euclidean embedding using the formula described here. And further down the road, there are other very interesting approaches that you can use in order to reduce the dimensionality, like locally linear embedding, described here with reconstruction errors, and SNE and TSNE as a way to have a like stochastic neighbor embedding. Those are the more sophisticated approaches. The most commonly asked questions that invite follow-up questions are PCA and SVD. So if you have them in mind and at the top of your head, that's always good, a good starting point in your interview. With that in mind, we go back to the concise answer. How do you combat the curse of dimensionality? Manual feature selection, principal component analysis, multidimensional scaling, or locally linear embedding. And that's basically all to it for asking the question on how do you combat the curse of dimensionality.